Good afternoon. I'm Zhang from Samsung Research Institute, China, Xi'an. It's a great honor to stand here to present our cooperation paper with ByteDance. Today, I will talk about our work on SSD failure prediction. Okay, let's start. SSDs have played a more and more crucial role in many applications such as database, cloud, AI, and have been deployed on a large scale in data centers due to its high performance. Subsequently, SSD failures bring additional maintenance costs and more impact on storage performance and reliability, such as jet performance and long-tail latency. To monitor and analyze SSD failures, we collected large-scale SSD monitoring data, more than 51 million telemetry logs from Samsung SSDs. The failure lists and related information, such as handling methods, are also collected. The telemetry log has 85 customized attributes. It's more comprehensive than SMART with about 20 attributes. The attributes involve uncorrectable error, correctable error, read-write, and so on. Based on telemetry logs, SSD failure prediction as a proactive fault tolerance mechanism can reduce the impact and cost of failures by funneling and handling them in advance. Failure prediction usually has 3 steps. The first step is feature engineering, which aims to extract key information from raw data. Feature selection is a common method to select important attributes related to failures from original various attributes. In this paper, we propose mutation extraction to capture failure-related information dynamically and accurately. In the second step, a machine learning algorithm is usually adopted to distinguish the failure patterns from health patterns based on the features. Classification algorithms or anomaly detection algorithms are often used. This paper adopts a similarity measurement existing in both algorithms to give full play to their advantages. Finally, failures are alarmed and handled according to the prediction results. We propose failure rating and diagnosis to provide more information to operators for failure handling. The proposed overall scheme is mutation similarity-based failure rating and diagnosis scheme. We call it MSFRD scheme. We first analyzed each of these steps to identify the challenges. First, feature engineering. We found that feature importance and data range change over time. In practice, model training is usually based on early data, and then the trained model needs to be evaluated for several months before it can be finally put online for failure prediction. This leads to a time gap between training data and the online testing data. Some failure-irrelevant attributes in training data may become failure-relevant in testing data. However, traditional feature selection relying on training data cannot adapt to these changes. For example, E2E uncorrectable error may not be selected based on early training data, but actually useful for online prediction. Then we analyzed the telemetry data trends to understand what is the key information related to failures. We found that field SSDs usually have real sudden rapid changes in telemetry attributes before the failures. We call them mutations. For example, finger A and B show that some field SSDs have real and rapid increase of non-UCC or read recovery attempts. Some healthy SSDs also have some increases, but the iterations tend to be slow. Most of the mutations are rare and likely to appear on field SSDs, but there are also some exceptions, such as WAF mutation in finger C. WAF is susceptible to workloads, so its mutation is common. In conclusion, telemetry mutations are abnormal changes, especially rare mutations, which are more likely to appear before failures occur. To capture key mutation information, we designed a dynamic mutation feature extraction approach. Compared with normal slow changes, mutations are rare, sudden, and unexpected changes. When a mutation occurs, the trend will deviate greatly from the expected normal trend. Therefore, we train a time series prediction model, informal model, with large-scale normal data, and use it to predict the normal trend based on historical trend. The difference between expected normal trend and the actual trend is considered as the mutation features to represent the degree of mutation. Dynamic mutation extraction has two benefits. First, for normal slow changes, the difference between expected trend and actual trend will be very small, and the feature values tend to be zero, so they are implicitly eliminated. The right finger shows there are few attributes with mutations, so other irrelevant and noisy data are reduced. Second, the mutations are extracted in real time. Even if some attributes are not related to failures in historical training data, their information will still be extracted when they change abnormally in future online data. This is better than static feature selection. In addition, we also suggest estimating the rarity of mutations to reflect their importance for identifying failures. Next, for building the machine learning model, we found that the main challenge in practice is that unseen data patterns would appear. For example, in the finger, besides the patterns already seen in historical data, in future data, unseen data patterns have appeared. They are far away from historical data patterns and may need to be pursued separately. Though the unseen outline patterns vary greatly, they may also have certain tendency on the distances to historical health and failure patterns. For example, in the finger, the unseen outline patterns of the healthy SSDs are closer to the historical health patterns than to historical failure patterns. So in practice, we need to distinguish patterns that have been seen in historical training data and identify unseen patterns as well. Previously, there were two main algorithms used for failure prediction: classification and anomaly detection. Classification algorithms are good at distinguishing health and failure patterns already seen in historical training data. Anomaly detection algorithms are good at identifying outlier patterns, including unseen patterns, but outlier patterns are not exactly equivalent to failure patterns. To take the advantages of both classification and anomaly detection algorithms, we adopt a similarity measurement idea exists in both algorithms. First, the patterns that seen in historical data can be effectively distinguished by measuring their similarity with historical health and failure patterns. Second, the similarity measurement can capture unseen patterns which tend to be outlier, and is helpful for estimating their health failure tendency. Next, the last step, failure alarm and handling. We analyzed the failure lists and found that SSD failures have various phenomena and degrees, in addition to serious failures. Some SSDs were reported to the failure list, but after confirmed by operators, they will walk out later, so they were not replaced. We call these failures gray failures, such as temporary performance degradation. This is mainly due to the complex fault tolerance mechanism inside the SSD. For example, read cry can fix some errors, but it may cause long-tail latency. As shown in the table, almost all of fuel SSDs with uncorrectable errors are replaced. However, the replacement rate of other SSDs is not so high, indicating that some of them have gray failures, such as performance degradation, and are not replaced. Therefore, fine-grained failure identification is meaningful to reduce unnecessary measures on workable SSDs, and internal errors, especially unavoidable ones, can reflect the failure level and status of SSD. To identify fine-grained SSD data, we suggest failure rating and progressive diagnosis. 4 levels are defined from serious failure to perfect health. Level 1 is serious failure, such as unavailability or data integrity failure. The field SSDs that are replaced or have unacceptable errors are in this level. Level 2 is gray failure. Other SSDs in failure list are usually available SSDs with gray failures. Level 3 is problematic health with self-warning or uncorrectable errors, but have unnoticed impact. They are not reported in failure list. Level 4 is perfect health without any issues. Historical SSDs are divided into these 4 levels. The level of a new SSD is determined based on the similarity of its mutations with the mutations of the SSDs of 4 levels. Then failures can be handled incrementally based on the level. Based on the above designs, the overall architecture of MSFRD is shown. There are 3 steps. First, to characterize the key failure symptoms, the mutations in attribute trends are dynamically extracted. The difference between the expected trend and the actual trend are used to represent the mutation. Considering that failures and the corresponding mutations are generally rare, we also introduce self-learned weights in the model to measure the rarity of mutations. Second, we divided historical SSDs into 4 levels and adopt a similarity measurement to perform failure prediction. For a new mutation of SSD, the failure level of the SSD is estimated by measuring the similarity of this mutation to the mutations of failed and healthy SSDs of these 4 levels. Third, measures are provided based on the failure level to reduce maintenance overhead. Serious failures can be directly handled, and less serious failures would be gradually diagnosed and processed. Next, let me introduce the detailed process. First, mutation extraction and similarity measurement. For all attributes of each SSD, we extract the mutations and their rarity. For an SSD to be predicted, we calculate its mutation similarity to its historical SSD at a different level using the weighted Euclidean distance. The mutation rarity are used as weights to amplify the proportion of rare attribute mutations in distance calculation, because rare mutations are more important for failure prediction. Then the top 3 historical SSDs that are most similar to this SSD in each level are found, and the similarity scores are obtained. The SSD is more likely to be at the level with high similarity scores. Therefore, for each level, the average of the top 3 similarity scores is regarded as the base confidence score for this SSD. The base level scores reflect which level the SSD is more similar to. In addition to the base level scores, which level the SSD falls into also depends on whether it's more likely a failure, a health, or an unseen one. Therefore, we introduce the failure tendency, that is the sum of level 1 and level 2 base score, the health tendency, that is the sum of level 3 and level 4 base score, and the outlier tendency, that is 1 minus the global max similarity score, and use them to fine-tune the base confidence score. When the SSD is similar to historical field SSDs, its failure tendency will be larger than health tendency, so its score of levels 1 and 2 will be larger after fine-tuning. And when the SSD is far away from all historical SSDs, its outlier tendency will be larger, which is used to amplify its original failure or health tendency. In this way, both seen failure patterns with similar mutations in historical data and unseen patterns with large outlier tendency and slight failure tendency would be captured. Finally, progressive diagnosis and processing. After failure rating, the SSDs of levels 2 and 3 which would face grave failures or problems can be further tracked and diagnosed to confirm their impact and fuse status. We design automatic trend-based diagnosis to judge if the SSD is going to be more similar to level 1 historical field SSDs, and judge if the mutation of the SSD is getting worse. If so, the SSD will be further diagnosed as level 1 failure. We also recommend using some tools to check the SSD. For level 2 grave failure, latency monitoring is useful to check if there is a performance drop and whether it is acceptable. For level 3 problematic health, 4-disk scan can be used to check if there are data integrity errors and their impact. In this way, the fine-grained SSD status can be tracked and diagnosed to reduce unnecessary handling for workable SSDs. The above is the proposed MSFRD scheme. Next, its effectiveness is evaluated. We use 3 datasets in evaluation. 2 are our telemetry datasets, and 1 is Alibaba's public smart dataset. We divide each dataset into training set, validation set, and test set in chronological order based on the real scenario. In terms of evaluation metrics, besides widely used precision and recall, F0.5 score is also used. The F0.5 score is the harmonic average of precision and recall, and the precision has higher weight because it's more important to avoid too many false alarms in practice. In addition, accuracy rate is used in failure rating evaluation. We first compared MSFRD with existing 4 schemes on failure prediction. On all 3 datasets collected from different companies with different monitoring attributes and workloads, MSFRD outperforms the existing scheme, reinforced ensemble classification, autoencoder, and MATF, achieving the better results on 3 metrics. MSFRD dynamically extracts mutation features to locate abnormal changing trends in real time and capture failure symptoms more accurately, thereby achieving better precision. Furthermore, MSFRD captures failure patterns through similarity measurement and introduces outlier tendency to help to perceive unseen failure patterns. Therefore, it predicts SSD failures more comprehensively and improves the recall. Compared to smart dataset with only about 20 attributes, MSFRD has greater improvements on complex telemetry datasets with 85 attributes due to its powerful ability to extract key information and adapt to data changes. For failure rating, we compared MSFRD with 3 methods that can also perform 4-level classification. The MSFR without automatic trend-based diagnosis, and the whole MSFRD performs better than existing methods. The mutation similarity measurement, the tendency-based rating fine-tuning, and the progressive diagnosis contributes to the high failure rating accuracy. Next, the effectiveness of each MSFRD model is evaluated. First, the dynamic mutation feature performs better than raw data and static feature selection because it extracts the key information in testing data without relying on the data importance in training data. Second, the rarity-based mutation similarity measurement and the tendency-based rating fine-tuning further improves the performance. Finally, coupled with automatic diagnosis on subsequent SSD status, the whole MSFRD achieves the best result. The results show that each model in MSFRD is significant. This is an example where level 1 failure is correctly predicted and rated. With dynamic mutation extraction, only a few attributes of this SSD have mutations with deep color in this figure, while other attributes that are changing normally in the raw data are implicitly eliminated. In this way, the key information is captured. After the similarity measurement in mutations, this example is mainly similar with level 1 failures, and the similarity scores are high, so it's therefore rated as level 1. Finally, let me give 3 conclusions about our work. First, mutations in monitoring data are key information for failure prediction, and mutation extraction is meaningful for removing failure irrelevant and noisy data. Second, based on the key mutation information, similarity measurement as a simple but effective way can take advantage of both classification and anomaly detection algorithms to capture failures more comprehensively. Third, more detailed SSD status can be provided by failure rating and diagnosis to help operators deal with failures accurately. Okay, thanks for listening. I'm open to questions.